Swayam Prabha. Digital India. Educated India.
So welcome to tutorial 3, which is about applications. The earlier two tutorials were more about fundamentals on structural materials, but this tutorial is about applications of these structural materials. So let's have a look at the tutorial. The first problem is about wear resistance of a steel gear. So that wear resistance is to be improved by hardening its surface. Now when we talked about heat treatment, we mentioned this carburizing or basically increasing the alloy content of the surface alone is possible, and so that increases the wear resistance of the steel gear. So if you do some change in the microstructure, if you achieve some change in the chemical composition of the surface of the material, surface of the gear, then it would be one will be able to achieve a very high wear resistance at the mating surfaces. So this is to be accomplished by increasing the carbon content within an outer surface layer as a result of carbon diffusion into the steel. So this is the case of case carburization. The carbon is to be supplied from an external carbon rich gaseous atmosphere at an elevated and constant temperature. So the temperature is very high, maybe 1000 to 1100 degrees centigrade, 1200 degrees centigrade, and it is maintained constant. So the diffusion of carbon occurs at very high temperatures. The initial carbon content of steel is about 0.2 weight percent, whereas the surface concentration is to be maintained at 1 weight percent, right? So you want to raise the surface concentration to 1 weight percent. Now note that carbon percentages up to 2% constitute steel, and beyond 2% we call it cast irons. So the carbon weight percentage at the surface of the steel gear is to be maintained at 1% of carbon. Everywhere the carbon percentage is otherwise, original carbon percentage is 0.2 weight percent. So you have taken a gear, or you have taken a disc of steel which has 0.2 weight percent carbon, machined it into a gear, so you have shaped it into a gear, and now you want to increase the hardness of the surface of this gear. So you want to raise the carbon percentage on the surface of the gear from 0.2% to 1%. At the rest of the mass or the rest of the bulk of steel, the carbon percentage is 0.2%, except for the surface where you want to raise it to 1%. So for this treatment to be effective, a carbon content of 0.6 weight percent must be established at a position 0.75 mm below the surface. Specify an appropriate heat treatment in terms of temperature and time for each of the temperatures 900 and 1000 degrees centigrade. Iron is austenitic, meaning face-centered cubic structure both at 900 and 1000 degrees centigrade. Now the point here is that in order to obtain 1% of carbon content at the surface, at 0.75 we have been given a carbon content of 0.6 weight percent. Okay, so there is a gradient of carbon percentage from the surface to the interior. So it is not a step change from 1% to 0.2% at an interface, otherwise that also would be disastrous. So there is a continuous gradient. So a certain thickness will have 1% carbon, and as you go inwards, the carbon percentage will continue to reduce, and it will reduce to 0.2%. So there will be a small region of transition from 1% carbon to 0.2% carbon. So you will not have just one single interface, one single plane where there is a step change or an abrupt change from 1% to 0.2%. So what we are being told is that at a position 0.75 millimeter below the surface, the carbon content is 0.6%. So this also means that the case depth, that is the depth of the hardened layer which has 1% carbon, is less than 0.75% thick, which means that the thickness of the case or the thickness of the hardened layer with 1% carbon is very, very small. It is of the order of fraction of a millimeter, maybe half a millimeter or even less. So with this we will now go to solve the problem. So the relationships which we will use are as follows. So you have this relationship giving you the concentration of carbon at different locations. So Cx is the percentage of carbon below the surface at x mm below the surface. C0 is the average composition of carbon, which is 0.2 weight percent in this case. Cs is the concentration of sorry, just a minute, let me read this. Concentration at a distance x from the surface. So this is what I have said, and C0 is concentration at t equal to 0 for all x. So C0 is a concentration at all times. Okay, so we need these equations where Cx is the concentration of carbon at a distance x below the surface. C0 is the average concentration of carbon. In our case it is 0.2% carbon. Cs is the concentration of carbon at the surface. So here we intend to have 1% as the concentration of carbon at the surface. So the denominator is 1 minus 0.2, so denominator is 0.8, and then Cx minus C0 is something that we need to so Cx is the carbon concentration at 0.75 millimeter below the surface. So if you take that, so in this what we are trying to do is that based on the left hand side that is known, we need to find out a time for which the heat treatment needs to be given. So we are given two temperatures, 900 degrees centigrade and 1000 degrees centigrade, and we have been asked to find out for how long the material should be exposed to the gaseous environment, carburizing environment, so that we can have at 0.75 millimeter below the surface a carbon concentration of 0.6 weight percent. So that is what we are doing here. So here you have 0.6 weight percent at x equal to 0.75 millimeters. So 0.6 minus 0.2 is 0.4, and here denominator is 0.8. So you have half, that is 0.5 on the left hand side, and then that is equal to 1 minus error function x upon 2 root dt. So d is the coefficient of diffusion which is calculable from this equation. So d is d naught exponential minus qd by rt, where the qd is the activation energy for diffusion for carbon in face centered cubic structure, which is 148,000 joule per mole. So that is what is given, qd. R is the gas constant. So since we are dealing with 1 mole of material, okay, so we need to calculate the value of d, capital D, that is the temperature dependent diffusion coefficient. This d naught is the temperature independent pre-exponential for carbon diffusion in FCC, which is given as 2.3 into 10 to the power minus 5 meters square per second. So now if you look at the units, for the right hand side, you will find that the distance x has to be taken in meters and not in millimeters. We have been given that the distance is 0.75 millimeter below the surface, so that 0.75 has to be converted into distance in meters, and the rest of the units are in joules, mole, the degrees Kelvin. So the right hand side, QD by RT is dimensionless, so you have d diffusion coefficient having the same dimensions as d naught. Now on the right hand side you have x upon 2 root of dt, and you see that the error function of ERFZ is listed out here for different values of z. Now what we have got here is left hand side as 0.5, so ERFZ is essentially 0.5. So because if you take this to the left hand side, then you get 1 minus 0.5 as 0.5. So ERFZ is 0.5. So now we need to find out the value of z at which ERFZ is 0.5. So it lies somewhere in between. So let us look at the solution here. C0 is 0.2, CS is 1, and CX is 0.6. So many meters, and then so D0 turns out to be so much, because it is so much square meter, because it has 10 to the power minus 5 if you see. Then QD is 148000. So all this data is given, and so the diffusivity at 1000 degrees centigrade is this so much, and at 900 degrees centigrade it is a little less. So the diffusivity is an order of magnitude higher, almost not all exactly, but significantly higher at 1000 as compared to 900. And capital X by interpolation works out to, because here you have one value at 0.45, z equal to 0.45, another value at of 0.52 at z equal to 0.5. So naturally for the right hand side, that is ERFZ, to be 0.5, the value of z has to be between 0.45 and 0.5. So that is why we have taken the linear interpolation between the two, and we have got x equal to what do we mean by x? X is the argument of the error function. So okay, so based on interpolation we have found capital X, which is essentially this value. So the right hand, the argument of ERF, which is x by 2 into root of dt. So we have got this value of 0.477, and x, this small x is equal to 0.75 millimeters, which is 0.00075, and then capital D is given here. D at 1000 and D at 900 have already been calculated. So for different temperatures we substitute the appropriate value in order to get the time for which the material should be exposed to get a case carburizing up to 1% carbon at the surface. So based on this equation, T is the where T is the only unknown, that is time is the only unknown, the time at 900 degrees centigrade is so many seconds. Our unit for time is seconds. So our units for time is seconds, because here in the equation we have based on our calculation for x, for example x, which is the small x, which is taken in meters, and d is the diffusion coefficient, which is taken as meters square per second, square meters per second. So now this when time is taken in seconds, it makes the argument of the ERF dimensionless. So x in meters and time in seconds makes this capital X dimensionless, and so based on that we have the value of time for 900 degrees centigrade as so many seconds, which means it is more than 29 hours of exposure to the heat treatment or the carburizing atmosphere. Whereas at 1000 degrees centigrade, you require much smaller time in terms of seconds, which translates to close to 9 hours, 8.88 hours. So close to 9 hours. So the relationship is not linear. So if you look at 900 and 1000, the difference is just 100 degrees centigrade, but the difference in the time of exposure is quite significant. So basically this shows that the relationship between the temperature and time is highly nonlinear. So it is always beneficial to do the heat treatment at higher temperatures rather than keep it for a long duration at lower temperatures. Of course, there are many other considerations in this. For example, the volume expansion, the rate of volume expansion. So if we are to take care of those issues, then a relatively slower heat treatment may be better in terms of the ductility of the material when we finish the carburization and we quench the material. So basically what it means is the volume changes or dimensional changes after cooling can induce lot of stresses in the material, and therefore if you have finished the heat treatment very quickly and you are quenching it from a relatively higher temperature, the volume changes and the dimensional changes will occur that much rapidly and to a greater magnitude, because quenching from a high temperature will result in a higher dimensional change, and it can induce stresses in the material. So depending upon the composition of the material and the ductility of the material, one has to judiciously take a decision of whether quenching should be done or the heat treatment should be done at 900 degrees centigrade or at 1000 degrees centigrade. So it is not just purely these numbers and the quickness with which you can carburize the material that governs the choice, but it also has to do with the other considerations of the stresses getting induced in the material while doing the quenching operation or while cooling the material from that particular temperature. So even normalizing might be able to give you the kind of martensite, so it may not require any severe quenching, but still one has to be clear that the stresses induced during cooling are not going to be too high. So here is another problem where we need to identify based on the pictures we get under a microscope, the fractographs or basically fracture surfaces. So these fracture surfaces are shown at different magnifications. For example, the top fractograph is shown at a relatively small magnification, meaning it's more of a macrograph. It is not a microscopic graph, microscopic picture as we see in B and C, but here what we see is that it's a fracture surface, no doubt, and we are to identify the nature of fracture from the pictures and show the origin of crack orientation, origin of the crack or direction of loading wherever it is possible, right? So you have origin of fracture over here in this case, because you see that the so-called river patterns which are seen here as I move the cursor along these river patterns. So all these indicate the direction of propagation of the crack. So crack has originated here and is propagated in several directions. So when the crack initiates at the center, it will propagate radially outwards and giving out this kind of radially outward river patterns. So wherever these river patterns converge, that is the origin of the crack. Next thing what we observe is that not much of an energy is absorbed in these during fracture. So it's more of a brittle fracture because you have mostly planar surfaces. So what you find is that there is not much of ductility, not much of strain energy that has been absorbed, not much of plastic deformation has been undergone by the material before the crack completely propagated, and when two halves became separated. So here, due to the planar surfaces and relatively faceted structure, one can call this as a brittle fracture. Here in the second case, you have a very good representation of ductile fracture, and here so these circles are called as dimples, and these are the outcome of voids being generated with plastic deformation. As the plastic deformation takes place, the voids are generated around second phase particles, or I mean at different interfaces, or even within the matrix, and so these voids are the ones where which are an evidence of lot of energy absorption. So between two voids you have these ligaments, so the material between the two voids is called as a ligament, and these ligaments are the ones which will be absorbing the plastic strain energy. So before the crack propagates, the overload will result in plastic deformation, where some strain energy will be absorbed in deforming the intervoid ligaments, and finally when the ligaments break, they coalesce with each other, and then the fracture starts. Now this kind of configuration of these of the ligaments and the way they're aligned shows that it's a shear fracture. So the fracture has taken place not in a uniaxial tensile direction, but it's a shear fracture. So the fracture surface pertains to a ductile material being sheared. So it has undergone shear, and substantial amount of shear strain has been taken by the material, and the direction of shear is in the direction of alignment of these dimples. So this is a shear fracture of a ductile material, so it's a ductile fracture unlike the previous one, and so that's the interpretation of this micrograph. Now here you see that the so-called dimples are extremely fine, because so much distance is just 4 microns, so dimples are of very small size. Large size, if there are large size dimples, then it's an evidence of even higher ductility. So larger is the size of the dimples, more is the ductility. So if you have dimple diameter, dimple size as 0, then you will have brittle fracture, which is shown here. The small dimple size there is some ductility, and the shear fracture is of a ductile nature. Here you have mixed type of fracture, you have mixed features, you have some ductile features here, there are few ductile features in the form of dimples here, and then there are faceted features as well. So what it means is that the crack propagation was not through a ductile medium all the time, so it happened through some islands of ductility. So the crack got slowed down at certain regions and then moved rapidly at few others. So you have these facets which are present here. So these facets would result in relatively fast fracture, rapid propagation of the crack, whereas these areas of relatively high ductility, meaning dimples, the presence of dimples indicating plastic deformation, absorption of strain energy, would mean that the crack was slowed down in that region, and therefore there was some resistance to crack propagation offered by the material at various locations. So it's basically a mixed kind of fracture. It has got mixed features of ductility as well as brittleness. So by and large, I mean, ductile materials can be made to behave brittle depending on the temperature. So here what you see is a mixed mode of fracture, where the material is ductile, but then it has fractured in a mixed mode condition. Now come to the problem 3. It's about interatomic bonding, which is about ionicity in ceramics. So calcium fluoride is a ceramic, and it has got 89% ionicity, and it has got higher ionicity than magnesium oxide, which is 73% ionicity. Now the question is, why are ceramics brittle at room temperature? Because what we have just seen is that materials are ductile at room temperature. Many materials are highly ductile, they show lot of plastic deformation before they fail, but then ceramics are brittle at room temperature. And in which way are polymers and composites different compared to ceramics and metallic materials? Now we have seen there is some similarity between the ceramics and metallic materials in the form of bonding, the crystalline structure and so on, but the nature of bonding is different between ceramics and metallic materials, and it is far different from the nature of bonding in polymers, because polymers are always covalent bonds and they are chains of hydrogen, carbon and so on. So these are basically chain polymers, long chain or short chain polymers. Composites are mixtures of polymers, ceramics and metallic materials. So basically these are the differences between the three materials. So let's see a more detailed reply. So the solution is that we have ionic character which depends on the electronegativities of the two. So calcium fluoride, so you have a calcium as a highly electropositive element, fluorine as a highly electronegative element, and larger is the difference between the two electronegativities, there the percentage ionic character increases very sharply. So as you see here, percentage ionic character equal to 1 minus exponential minus 0.25 into xa minus xb bracket square into 100. So xa minus xb refers to the ionicity, electronegativity of A and electronegativity of B. So you have electronegativity of calcium, electronegativity of fluorine, and so you have the square of this. So this term ends up being positive all the time. So you have percentage ionic character depending on the difference in the electronegativities of the two elements. So if you take, let's say, sodium fluoride as compared to calcium fluoride, sodium fluoride will have a much higher ionicity. That is because sodium has got much greater electropositivity and so much lower electronegativity, and then fluorine has got very high electronegativity, and finally you will get a very high percentage ionic character. Now ceramics at room temperature have no ductility due to nature of the ionic bond. So ionic bond is something that has a certain strength, and if the strength is overcome, the ionic bond breaks. So it is either there or not there. Okay. So the interatomic forces are interionic forces are very high, and therefore the bond either exists or it is broken. That's it. There is nothing in between. Whereas in metals, the metallic atoms are held together by metallic bonds, which are bonds between electrically neutral atoms. So there is a slight distinction between ceramics and metals, namely that ceramics are bonded together between two ionized elements. So calcium and fluorine, they are ionized condition. So these are not electrically neutral. So these are two ions, and then they come together and they get bonded together. Whereas metals, each atom is electrically neutral, and therefore in metals bonding takes place between electrically neutral atoms. Now polymers are made of covalent bonds, and number of covalently bonded atoms of various elements including hydrocarbons and halogens, because you have PTFE, polytetrafluoroethylene, right? So you have carbon tetrachloride, CCl4, right? So you have hydrogen replaced by chlorine, basically halogen atoms. So these form a long chain to constitute a molecule, and the length of the chain determines the molecular weight and hence the strength and the melting point. So small is the molecular weight, smaller is the molecule, the flowability is easier, melting points are lower. Larger is the molecule, longer is the chain, then molecular weight is high and melting points are also high. So this is again unlike metals, where the metals have fixed melting point. So pure metal will have fixed melting point, but a pure polymer, let's say nylon 66 for example, will have melting point depending upon the molecular size of nylon. So that is a difference. And composites are made of either fiber or I mean they're a combination of fiber, that is either carbon fiber, glass fiber, basically fibers of organic materials, and either metal or a polymer. So you have either metal matrix composites or polymer matrix composites. So our CFRP, carbon fiber reinforced plastic, right? Carbon fiber CFRP, carbon fiber reinforced plastic or polymer, whatever you may call it. So so these are polymer based, whereas metal matrix composites are I mean they have these glass or Kevlar or carbon fibers in metallic matrix. The problem 4 is another interesting problem, where we have different diffraction angles for the first 4 peaks. So these are first order diffraction angles. So basically in Bragg's law you have 2d sin theta equal to n lambda. So there n is equal to 1. That is what it means. Which may have an BCC or FCC structure. So you want to find out whether it has BCC or FCC structure. A monochromatic X-ray radiation of wavelength 0.0711 nanometers was used, and what we have got is for different planar indices 1010, 200, 211 and 220, the diffraction angle 2 theta is so much, and we have been given the different structures of different elements, right, and their corresponding atomic radii. Now what we have to find out is what is the metal, okay, which metal it is. We have to identify the metal and the corresponding structure. So based on this data we have to do that. So first we have to get the interplanar spacing of each of these peaks based on each of these peaks, right. So you have you can find out the interplanar spacing, because typically given a structure, let's say FCC or BCC, and a given atomic radius, you will have a fixed interplanar spacing. So based on that we therefore identify the material. So our strategy will be to find out the interplanar spacing, the corresponding structure, and then identify what could be the atomic radius, and then based on that identify the material as given in this data sheet. So based on each peak determine the atomic radius. So that's what we are going to do. And what's the difference between simple reflection and diffraction? Why do metal crystals diffract X-rays but not visible light? So if you take C, it is the result of a small wavelength of X-rays, and visible light has got a much higher wavelength, which is much higher than the interatomic spacing of the material. Therefore it cannot get diffracted. So visible light doesn't get diffracted, whereas X-rays, which have got much smaller wavelength compared to the interatomic spacing or even the atomic radius, will get diffracted. And state and briefly explain one source of property anisotropy, each in a single crystal and polycrystals. Explain why anisotropy of properties may be different for HCP and FCC crystals. So this is what we have to explain. So what we need to for the last 2 parts, this data is not required. So for A and B we need the data. So the equations are here: n lambda equal to 2d sin theta. So HKL is the HKL of these planes is given over here: 110, 200, 211 and 220. And so we have n equal to 1, so lambda equal to 2d HKL sin theta. Now we have been given the value of lambda 0.0711 nanometers, and you have been given the sin theta, the angle theta, the angle of diffraction, because 2 theta is given, so one has to convert this into theta and use it. So many times people make mistake of using it as it is. No, it has to be divided by 2 and then only used in this equation. So you have to get the value of DHKL. Once you get the value of interplanar spacing for different planes, then you will get the interatomic spacing A, because you know the HKL and you will get the interatomic spacing A, or basically the lattice parameter A, right? You will get the lattice parameter A, and based on that we will be able to find out which material it could possibly be. Okay, so now having been given this 0.0711 nanometers as the wavelength, theta angle of diffraction here, then the theta radians is I mean the same thing converted into radians is given here, and the corresponding interplanar spacings are given for the four planes 200, 211 and 220. So these are the interplanar spacings for these different HKL values, right? And now the corresponding values of A based on these DHKL is 0.288. Now it is important that you get all four planes, I mean all four planes should lead to the same value of A, because all these four planes are a part of the same crystal, and therefore given a single lattice which has got a lattice parameter A, the DHKL and A have to be consistent with each other. So based on that, if you don't get this, if you don't get A identical for these four planes or similar, I mean up to the 3 decimals it's okay. So 0.288 nanometers is the lattice parameter you get. If you don't get this, then your data is inconsistent. Here the data is consistent because the interplanar spacing and gives rise to the same value of A irrespective of the plane for which we have found the interplanar spacing. Okay. Now we need to find out the value of A based on whether it is FCC, BCC or HCP, because now you have different lattice parameters for different materials, right? So for BCC lattice, what is going to be the radius, atomic radius is what we are going to find out. So lattice parameter is given here, and the corresponding lattice or the corresponding radius of the atom is 0.124 for BCC. For the same lattice parameter A, if the structure were FCC, it will be 0.1018, and for if the structure were HCP, we would get this. So we know the lattice parameter now, but we don't know what structure it is and what metal it is, right? So now we set out to find out a material which has got a BCC structure and this radius, right? So now we find that based on the four values of A here, we get about 0.124 as the radius and the BCC structure. So in this we have 0.1246 as the but this is nickel, which is FCC, but then here you have somewhere chromium which has got 0.1249, right, which is BCC. So you see that nickel also has got similar thing, but then it has got a FCC structure. So for FCC structure it is 0.101 or 102, 0.102, but here we don't find that. For FCC structure 0.102 we don't find. So chromium, the material is chromium, and it has got an atomic radius of 0.1249. So that is what we conclude based on this. If we were to talk about HCP structure, it can have the radius of 0.144 or 142 or 144, and so here what we find is that for HCP of 1445, it could be titanium as well. So it could so we have chromium and titanium. Just to substantiate my answer for this answer D, I have given some figures here. Wavelength of visible light is 400 to 700 nanometers. Wavelength of X-rays is 0.01 to 10 nanometers, and you see that the interatomic distances are fraction of a nanometer, and that is possible for X-rays to penetrate, because X-rays can have a wavelength of 0.01 to 10 nanometers, so it can easily get diffracted from or penetrate into a crystal with interatomic spacing or the lattice parameter of 0.288 nanometers. So that is why visible light doesn't get diffracted, it gets reflected, but X-rays can get diffracted. We come to the next problem. Compute the minimum value of plane strain fracture toughness required of a material to satisfy the leak before break criterion for a cylindrical pressure vessel where the hoop stress is given by sigma equal to PR by T. So this is the maximum principal stress, basically circumferential stress. The vessel radius R and wall thickness T values are 250 millimeters and 10.5 millimeters respectively. So thickness is 10.5 millimeters and the 250 millimeters is the vessel radius, and the fluid pressure P is 3 MPa. Assume the value of 3.5 factor for the factor of safety and the geometric factor of 1. Explain why the fracture toughness calculated by you will ensure leak before break. So that's what we now demonstrate. So P is 3 MPa, R is 250 millimeters and T is 10.5 millimeters, so that the sigma, the stress, circumferential stress is about 71 MPa, and then the factor of safety being 3.5, the design stress is of the order of 250 MPa. So what you have done is you have assumed that 250 MPa will be the stress coming on the pressure vessel instead of just 71.42. So you are over designing the pressure vessel by 3.5 times. So you have 250 MPa as the strength of the the stress that is coming on the pressure vessel. K1C is 45.4. So as given here, the K1C is 41.5 and therefore 45.4, and so the A critical is 128.65 millimeters, and so since the A critical is greater than thickness, leak before break criterion is achieved. Now if you take the factor of safety on K1C itself as 1.5, let's say K1C given is 45.4, but then if you assume that K1C itself is relatively smaller than what it actually is, then you get the you will get the A critical as 23.65 millimeters. Still the leak before break criterion is achieved, and even when K1C is taken as 1, so what it means is that you divide this 45.4 by 3.5, because you have taken 3.5 as a factor of safety. So you divide it by for when it is 1, then you have 10.5 millimeters as the thickness as A critical. So A critical being equal to thickness, leak before break criterion is barely achieved. Now one thing is that in each of these cases A critical is achieved. Now A critical is the size of the internal flaw, right? So the maximum size of the internal flaw that can be tolerated is 21 millimeters, so which is again greater than the thickness, right? 2 times A critical, which is 21 millimeters, is tolerated because A critical is so this is much more than flaw size is much more than the thickness. So here it is barely achieved, and a 21 mm size flaw can be tolerated, or slightly less than 21 mm flaw can be tolerated by the pressure vessel with K1C of the material of this magnitude, close to 13, let us say, right? So that's what it means. A structural component in the form of a wide plate is to be fabricated from steel alloy that has plane strain fracture toughness of 77 MPa root meter and yield strength of 1400 MPa. The flaw size resolution limit of the flaw detection apparatus is 4 millimeters. So the device which you have used to inspect the structure can detect a flaw which is 4 millimeters and no less. I mean, if the flaw is less than 4 millimeters, it will go undetected. So that is a risk that you are taking, right? So anything bigger than 4 millimeters is detectable by the flaw detection apparatus, and anything less than 4 millimeters will go undetected or will be seen as absent, right? So if the design stress is 1/2 of the yield strength, so basically your factor of safety is half. So factor of safety is 2 rather. Factor of safety is 2, meaning the design stress is half of the yield strength and the value of geometric factor is 1. Determine whether or not a critical flaw of this plate is subject to detection or not. So basically what it means is that if the size of the flaw is basically we want to find out whether the critical flaw size is more than 4 millimeter or less than 4 millimeter, right? Are stress intensity factor and fracture toughness the same? What do they represent? The occurrence of fracture represents a balance between the two forms of energies. Which energies are they? How does plastic deformation affect the stress at fracture and why? So here it is, yield strength is 1400 MPa, and so all these values are given. Now design yield strength is 700 MPa. So factor of safety is actually 2, and then what we have assumed here is that the yield strength used for calculation is half of the actual yield strength. So which means that we are assuming that material will yield at just 700 MPa and not at 1400 MPa. By this assumption, what we are achieving is that we will try to maintain the stress level below 700 MPa, right? And so we will never let the stress level reach 1400 MPa. So which means that we are not allowing any yielding to take place in the material at any point of time. So the critical flaw size is of the order of 3.8 millimeters, and so the flaw is unlikely to be detected. So if you take a flaw size which is slightly higher, if you take the flaw size which is not factor of safety that is slightly higher, okay, so a slightly higher factor of safety, we have taken 2 here, 2.25 can be the factor of safety, where you will get a flaw size of about 4.8 millimeters as a critical flaw size, right? So now this flaw size is detectable by our instrument. So so that's why one has to design the pressure vessel or the product, the structural component. Okay, one has to design a structural component taking a factor of safety of 2.25, so that if the flaw is not detected, the crack propagation or the flaw will not propagate and break the or it will not propagate and cause any damage to the structure. So if the critical flaw size is beyond 4.8, okay, or beyond 4 millimeters rather, now it is 4.8, if it is beyond 4 millimeters, then it will get detected and you will know that it is not acceptable, right? The flaw size is too big. But if the flaw size remains undetected, then it's a very great risk. So if you take a factor of safety of 2.25, then your flaw size of 4.8 mm, the critical flaw size that is detectable is 4.8 millimeters. Now if you don't detect any flaw, which means that flaw size is less than 4 millimeters, then it is not going to propagate, because the flaw size required for propagation is 4.8 millimeters. So anything smaller than that is not going to propagate on its own. So it will not cause any fast fracture. That's why it is safer to design with 2.25 as the factor of safety, so that any flaw that is risky can get detected. If the instrument shows that there is absolutely no flaw, it means that the flaw size is less than 4 millimeters, and that being much lower than the critical flaw size value, there will be no fast fracture taking place. Now K1C and stress intensification factor are different because the stress intensification factor indicates a multiple by which an average stress gets aggravated in the presence of a flaw. So normally when we calculate stress at a cross section, we take the force divided by the cross sectional area, and we assume that the entire cross sectional area is supporting the load equally and there is no flaw in between. Flaw is the one that causes stress concentration. So stress concentration means stress intensification. So if the flaw size is A, then we need to find out by how much is the stress intensification taken place relative to the assumed average stress of sigma naught. Sigma naught is load divided by the cross sectional area, where you are assuming that the flaw is absent. But now the flaw is present, unfortunately, and it has got a size of 2A, and so it's an internal flaw, so it has got size 2A. If it's a surface flaw, we take only A as the flaw size, and rho is the tip radius of the flaw. So if the smaller is the radius of the tip of the flaw, then you have a much higher stress intensification taking place. So if it's a very sharp crack, it's a very hairline crack, it has got a very small tip radius, so that's where the stress intensification is the maximum. Okay, so on the other hand, if there is a spherical flaw, if it's like a pinhole or blowhole or whatever, if it's a spherical flaw, then K is the stress intensification is equal to 2, because A, the flaw size is 2A, right? So the flaw size is 2A, so A is equal to radius, which is rho. So rho is the tip radius as well as the radius of the flaw. So that's why this A by rho becomes equal to 1, and therefore K is equal to 2. So so for an internal flaw of a spherical size, K is equal to 2, or spherical shape, the K is equal to 2. And for sharper flaws, smaller is the rho, greater is the intensification factor. K1C relates to the stress at which flaw of a specific size will propagate and lead to failure. So basically it relates to a fast fracture. Given a stress level, one can determine the critical flaw size that will propagate, leading to fast fracture. K1C indicates fracture toughness and relates energy absorbed during fracture. K1C for brittle materials would be small, that for ductile materials would be large. So it's the last problem, or maybe the second last one to be solved. It is known that kinetics of recrystallization for some alloys obey the Avram equation, and that the value of n in the exponential is 5.0. If at some temperature the fraction recrystallized is 0.3 after 100 minutes, determine the rate of recrystallization at this temperature. So let's look at the situation. You have n is 5, okay, so the exponent n is 5, and 0.3 is the one recrystallization after 100 minutes. So according to the Avram equation, you have y equal to y is fraction transformed, that is fraction recrystallized, equal to 1 minus e raised to minus kt raised to n. So now exponential has got a minus kt raised to n, right? So t is the time which is raised to n. So you have time in minutes, and that is raised to 5. So what you see here is 0.3 equal to 1 minus e raised to minus kt raised to 5, and this is equal to 0.7, right? Fraction transformed is that is because it is 1 minus 0.3. So e to the power minus k into 100 is to 5 is 0.7, because it is 1 minus 0.3, 30% is transformed. So this is basically the untransformed part. So minus k t raised to 5 equal to, so if you take ln on both sides, ln of 0.7 is equal to minus k into 100 raised to 5, and therefore k is given as, I mean k is obtained as this value 10 to the power minus 11 into this. Now at this point we have to find out what happens, because what we have to find out is determine the rate of recrystallization at this temperature. So at what temperature? At some temperature. So at that some temperature, the rate of recrystallization has to be found out. So the point at which we take this rate is when the transformation is to the extent of 50%, right? So for y equal to 0.5, we take we would like to find the time, okay? We would like to find a time, and then we can get the rate of recrystallization. So we have therefore time of 114.2 minutes. So the rate of recrystallization at this temperature is 1 by T, right? And so that is 1 upon 114.2, which is 8.76 into 10 to the power minus 3 per minute. So that is the rate of recrystallization. So the noteworthy point is that we take the rate of recrystallization at a point where 50% of the transformation has taken place, and we need to find out therefore the time that is needed to cause a 50% transformation, and 1 divided by that time is the rate of recrystallization at that particular temperature and the extent of transformation. So this is the last problem. A single crystal of metal that has an FCC crystal structure is oriented such that a tensile stress is applied parallel to the 100 direction. If the critical resolved shear stress for this material is 0.5 MPa, calculate the magnitudes of the applied stresses necessary to cause slip to occur in the 111 plane in each of the 1 bar 10, 101 bar and 0 bar 11 directions. So these are the, so you have the slip plane as 111 plane, and the directions are these. So these directions should lie on this slip plane. That is a very important criterion. So what it means is that if you would like to check the product of this 1 into 0, 1 into minus 1 plus 1 into 1, that should so that this sum of these products should give you 0. So here also you have 1, 0 and minus 1. So 1 plus 0 minus 1 gives you again 0, and here 1 minus 1 and 0. So therefore this also gives 0. So basically what it means is that 111 plane and these directions are mutually orthogonal, meaning 111 direction is perpendicular to the plane and these are in the plane. So basically for slip to occur, these directions have to be in the plane. So that is what one has to check. Now the stress is applied parallel to 100 direction. Stress is not applied perpendicular to 111 direction or 111 plane. It is applied parallel to the 100 direction. So basically it is applied perpendicular to the 100 planes, right? So now we have this solution. Tau critical resolved shear stress is 0.5 MPa, and the angle is between the U1, U2, V1, V2, W1, W2. So this is basically the angle between 100 plane and 111 plane, because stress is applied parallel to 100 direction, and we want to find out the stress, the shear stress in the 111 plane and in these three directions. So basically we need to find out the angle between the two. So phi is equal to cos inverse of 1 by root 3, which is 54.73 degrees. Now for a slip direction 11 bar 0, we need to find out the angle between 100 and 11 bar 0, and then based on that then we get sigma y equal to that is the stress is equal to tau CRSS upon cos phi cos lambda, and that is 0.5 is the tau CRSS, and that is 1.224 MPa. So the stress of 1.224 MPa will cause slip along plane 111 and in the direction 11 bar 0. Similarly, for 101 bar the same stress will cause slip in this direction as well, and then here you have cos inverse of 0, right? Cos inverse of 0, and therefore the critical resolved shear stress will be 0 irrespective of the stress applied. So this will always slip. So basically this is how the problems are to be solved. So you must have got an idea about how to deal with different situations, and hopefully you will be able to understand why things happen the way they do in real practice. You will be able to understand the reasons behind the industrial practices used. So with this we come to the end of the tutorial. Thank you.